Hello everyone, my name is Stephen Mispilkin, and I've chose to do my report on PLA, which is polylactic acid or polylactide. It's a biodegradable plastic. PLA, it's a biodegradable polyester made of lactic acid monomers. At the top right, you can see one of the lactic acid monomers. Two monomers will come together and undergo a condensation reaction, and water will leave, and they will join together via an ester linkage. And this can go on for many times, since the N outside the brackets means it can go on however many times you wish the reaction to occur. It was invented by Wallace Carruthers in the 30s at DuPont, just like many other products that were developed, polymer products that were developed in the DuPont company at that time. Nylon and neoprene were also come up with by Wallace Carruthers, although he couldn't find a way to mass produce it at the time, so it wasn't widely used until the 80s by the Cargill company. Unlike other plastics, it's derived from renewable resources like corn, sugarcane, tapioca, and other starch products. It can even be derived from organic wastes like compost piles, in which the starches can be refined out. Starches are then fermented by bacteria to form the lactic acid monomers. And because of its organic structure, it can also be broken down in the reverse way if certain conditions are met. The polymer itself is not patented, but some companies have chosen to add additional side groups to make it more stable, and those are patented. And some companies have also patented the technique to isolate the polymer. And here's just a few details about the compound itself. The chemical formula is C3H4O2, and the N stands for the amount of monomers you want to join on. The molecular weight per independent monomer is 72.06 grams per mole. The density is 1.31 to 1.39 grams per milliliter, and the melting point is between 150 and 160 degrees Celsius. PLA is widely used in many different aspects of the lives. Up here you can see like the plastic cups. They can biodegrade in the environment over time. Agriculture, they can use it for these mulch rows that keep moisture over the seeds and plants or roots to help them grow better. It can be woven into fabrics that are also UV resistant, so like curtains that block the heat or UV rays from entering the houses. These salad containers are more plastic that are made by them. Fishing line and 3D printing wire here, and it can even be used at the top for biomedical reasons. Like these are orthopedic screws where they can actually screw bones together once they break, and slowly over time, within a year, maybe up to 2, they'll slowly deteriorate in the body naturally over time and form lactic acid, which the body can then reabsorb. And down here, they're investigating its properties because PLA can be printed in a 3D printer to form a scaffolding, and then independent cells can be placed around to grow tissues, which can then be implanted into a person or grow inside a person, and once inside the person, it'll break down the scaffolding and leave the tissue behind. And here you can see the basic condensation reaction. You have 2 molecules of lactic acid. One hydrogen leaves with the hydroxyl group of the other, and the leftover oxygen forms the ester linkage between the 2 monomers. And this can go on and on depending on the concentration of reactants because of the free hydroxyl ends at either end of the polymer. You can see here, this is the complete mechanism for it. These are 2 lactic acid monomers. One hydroxyl group attacks the carbon of the carboxyl group because it has a slightly electropositive charge, and as that happens, the double bond breaks, forcing electrons onto the oxygen, giving it its negative charge. This reaction takes place under heat to give it the energy it needs. The hydroxyl group of the first one makes a bond with the hydrogen proton, and electrons move to the oxygen there, as you can see down here. And then oxygen electrons on the negatively charged oxygen reform the double bond and cleave off the water. And as you can see here, the ester linkage between the 2, and water is released. This will typically be done under vacuum filtration to remove the water, because water can affect the density of the product and make it less stable. This type of synthesis is more widely used because the chemistry can be more controlled and the water can be better vacuumed out of the system. Also, on the previous mechanism, you can see two monomers attached to each other side by side. In this way, they create an intermediate ring where all the hydroxyls take part in the reaction, and two ester bonds are formed to form the lactide ring. Catalyst, a metal catalyst, is shown here, tin octanoate, cleaves the ring and leaves the polymer of PLA, and depending on the amount of reactions, again, you can create a chain as long as you like. And here you can see the exact mechanism that occurs. It's just like the first one, however, both hydroxyl groups attack the partially positive carbon inside the carboxyl groups of each monomer. It's the same reaction mechanism that forces the electrons out to the oxygen, and the HOH bond forms outside, and then oxygen reforms the double bond and water is cleaved off. There's two molecules of water because one on each side has come off of the compound. It then forms this diester bond. This is known as a lactide ring, which then undergoes another reaction using the tin octanoate discussed in the previous slide to cleave the bond and form the PLA polymer. And this can be done just like previously with as many reactants as you wish to form your product. Since it's listed as a biodegradable molecule, I thought it was important to include how it might degrade, and simply the water can cleave the ester bond and reform the hydroxyl groups on either side, forming the lactic acid monomers, which can then be used by other organisms or uptaken by something else, or even reused inside the human body. One of the reasons I chose this molecule is because it's listed as environmentally friendly. It can take up to 80 years under natural conditions, which still is a very long time, but considering other alternatives of plastics that can take hundreds, thousands, or more years to break down, it's a pretty good step in the right direction. On closed industrial systems where they can monitor the pH and the amount of moisture in there, or the microbes that come into contact with it, it can take as little as a few days to break down, up to a few months to break down, depending on the conditions. Like a bunch of you, I'm pursuing a medical geared degree, so the biomedical impacts of this polymer greatly interested me. The fact that you can 3D print like a scaffold to grow live cells on and develop whole tissues, which can be grown either in or outside the body, but once it's put in the body, the scaffolding will degrade into the lactic acid monomers, which can be reused by the body or expelled, but it leaves behind the healthy tissue. So it has wide implications that could possibly one day regrow human organs for people that need them. The diversity of this product is just extraordinary. And that's my project on PLA. If you have any questions, let me know.